LiREC-Net, a target-free, learning-based network for jointly calibrating 3 sensor modalities, LiDAR, RGB, and event cameras. This work was funded by the Federal Ministry of Research, Technology, and Space Germany, BMFTR, under the project Scene understanding is at the heart of every modern autonomous system, self-driving cars, drones, mobile robots. They all need to perceive and reason about their environment in real time. Robust autonomous perception relies on fusing complementary sensors. RGB provides dense color but lacks reliable 3D and fails in low light. Event cameras offer high dynamic range and low latency, but no color or depth. And LiDAR delivers accurate 3D independent of lighting but is sparse and colorless. Since each modality compensates others' limitations, effective fusion requires accurate calibration to align their data. Calibration is therefore a prerequisite for fusion. LiREC-Net takes miscalibrated RGB, LiDAR, and event inputs and outputs geometrically aligned modalities. It jointly learns calibration for all 3 sensors in a single, target-free network without checkerboards or dedicated scenes. The method combines LiDAR point-based and projection-based representations for improved robustness, while being efficient and accurate. We assume RGB and event cameras are pre-calibrated, with miscalibration occurring only in LiDAR. Here is the overall architecture. 2 branches share a common LiDAR backbone, with the upper branch handling LiDAR RGB calibration, and the lower branch handling LiDAR event calibration. The model includes modality-specific feature extractors, a shared LiDAR processing path, cost volumes for cross-modal similarity, and fully connected layers that regress the calibration parameter. Looking at the inputs more carefully, the first branch takes a monocular RGB image, while the second branch takes an event frame. These are the 2 image domain inputs we want to align LiDAR against. Notice that both branches feed into the same architectural skeleton. The only thing that changes is which image domain modality we're calibrating to. Both branches use LiDAR in 2 complementary forms: the raw point cloud, processed with point-based features, and a depth map obtained by projecting LiDAR into the image plane via scaled depth projection, SDP, using camera intrinsics. The key idea is that the same LiDAR input is shared across branches but exhibits different drift relative to the RGB and event cameras, so each branch predicts its own calibration correction. Zooming in on the feature extraction modules, we use MVIT2 for all image domain inputs, including RGB, event frames, and LiDAR depth maps. MVIT2 is a multi-scale vision transformer that provides strong hierarchical features at multiple resolutions, which is crucial for constructing the cost-volume layer. On the LiDAR side, we extract point-wise features using Point Transformer v3, a state-of-the-art and efficient method for scalable point cloud feature learning. These features are then concatenated with projected depth features from MVIT2, resulting in a rich, geometry-aware LiDAR representation shared by both branches. Finally, each branch builds a cost volume, a correlation layer that explicitly measures the local similarity between the LiDAR features and the corresponding image domain features. The cost volume is then passed through a stack of fully connected layers that regress to outputs, a translation vector and a rotation quadrant. During training, the losses from both branches are summed with equal weights, so the network learns to calibrate both pairs jointly. The losses consist of point cloud distance, translational, and rotational losses. Now we briefly discuss training and inference. We explain here a 5-stage iterative refinement scheme, starting from the miscalibrated input. Each stage predicts a residual correction, updates the estimate, and forwards it to the next stage. All stages are supervised with ground truth. By the final stage, the calibration error is significantly reduced, as shown in the quantitative results. Here are the quantitative results and key takeaways. On KITI, LiREC-Net achieves 1.80 cm translational error and 0.11 degrees rotational error for LiDAR RGB calibration, comparable to dedicated bimodal methods such as pseudocal and LiREC-Net, while also handling LiDAR event calibration within the same model at similar accuracy. On SEC, we report results in both 2-stage and 5-stage settings. Importantly, compared to separate bimodal networks, our trimodal model matches accuracy while using fewer parameters, lower inference time, and reduced GPU memory, demonstrating the efficiency of joint learning. Some qualitative results on SEC are shown here. The upper row illustrates LiDAR RGB calibration, while the lower row shows LiDAR event calibration. The key observation is consistency, despite varying initial miscalibration across scenes. LiREC-Net achieves accurate alignment in all cases in the upper row. In the lower row, under a single miscalibration setting, the alignment remains consistent across both modality pairs. This demonstrates the desired joint, modality-consistent behavior of the architecture. We assume that transformations differ due to independently applied perturbations to the LiDAR, and the same qualitative behavior carries over to KITI. Again, the upper view shows consistent calibration across varying miscalibration errors, and the lower view shows consistent calibration with fixed miscalibration errors. The takeaway is that LiREC-Net generalizes across to quite different datasets.